Okay, so today we're looking at rational numbers. So get the heading down, lesson objective keywords, dates in Welsh. Dates in Welsh, especially for you, Lewis, in your book. Do it now. Hit pause when you're ready to have a go at the starter, hit play again. Okay, so we've got our starters for today, 3 questions. Hit pause, have a go. When you're ready, hit play again and we'll go through the solutions. Okay, hopefully you've had enough of an opportunity to go through them. First question is £240 shared in a ratio of 5 to 3 between friends. How much do they each receive? Now, I always tend to use the three steps: add, divide, multiply. So we add the ratios, 5 plus 3, giving us a total of 8 shares, and then we divide £240 divided by 8, or over 8. It gives us, sometimes it's 8 going to 240, 30 times. So each share is worth £30. Now the shares are divided into a ratio of 5 to 3, 5 shares and then 3 shares. So we multiply by the amount per share. That gives us £150 to 90. Okay, I like using the 3 steps, add, divide, multiply, when I'm sharing a given ratio. Okay, let's have a look at the second question. X squared minus x minus 56 is equal to 0. So I take my minus 56. My x squared does not have a coefficient, so I've got minus 56. I need to find the factors of minus 56 that can give me minus 1 when I add them. So what do you think? 7 and 8? 7 times 8 gives me 56. One of them has got to be negative. Because it's a minus x, the larger number has got to be negative. So in brackets I've got x, and I've got another x here, equals 0. And I think I've written them in the wrong place, but never mind. So this is plus 7 and minus 8. So that implies then that either x plus 7 is equal to 0, or x minus 8 is equal to 0, which means that either x is equal to minus 7 or x is equal to 8. This one, how many people spotted straight away that it was a difference of 2 squares? So we haven't got a middle term, we haven't got a term in x, so that means this is a square number or squared term. This is a squared number, and it's 49 is the square of 7. So if I have x plus 7, I also have x minus 7 equals 0. So either x plus 7 equals 0 or x minus 7 equals 0, which means that either x is equal to minus 7 or plus 7. Okay, and finally, express 300 as a product of prime factors. And when I'm going into prime, I like to know what my prime numbers are. 1 is in the prime number, 2 is, and 3, 5, next one, 7, 9 isn't because 3 goes into 9, then 11, and then 13. And I'm going to stop there. I think that's enough to start with, to be getting on with. And I put my 300 here. I put my branches out there. Try the smallest number. Does 2 go? Yes, it does. 150 times. I circle my 2 because it's a prime number, and I leave that alone. And I put my branches on 150. Does 2 go? Yep, 75 times. Circle that. Now 2 doesn't go into 75 because it doesn't end in an even number. Next number is 3, so I try 3. Will 3 go into 75? Yes, it will, because 7 add 5 is 12. And 12 is in the 3 times table, so I know that 3 will definitely go in there, and it will go 25 times. Try again. Oops, sorry, I need to circle the 3 because it's a prime number. 2 doesn't go, it's not, it doesn't end in an even number. 3 doesn't go because 2 add 5 gives me 7, but I know 5 times 5, 25 is a square number. So to finish, you can't just leave it like that. These are your workings, so you have to write 300 is equal to 2 2's, so 2 squared times 3 times 5 squared. You have to write it like that and make your multiplication symbol obvious, because too many people are writing plus there. Okay, and that's your solution to number 3. Okay, good. So I want you to mark it in green, rag it, and then when you're ready, hit play again, and we'll move on to rational numbers. Okay, so we're looking at rational numbers today. What are rational numbers? And they are numbers that can be expressed as a fraction. Any number that you can express as a fraction is a rational number. Now, where does that fit in with all our numbers on the number line? Well, all numbers can be represented on the number line, okay, and we call them real numbers. Now we start with the natural numbers. Natural numbers are what we use to count 1, 2, and 3. Now, if we think of these as a Venn diagram, and these are sets, so this is a set of natural numbers. The next set that includes the natural numbers is that of whole numbers. So that's the natural numbers plus the 0. So that's our whole numbers. Then the next set, which includes whole numbers and natural numbers, are the integers. So now we've introduced the negative numbers. So negative numbers and the whole numbers. So you can see now how our number line is looking. And then we have our rational numbers. And these are all the numbers which we can express as fractions. So they include your fractions here, they include your decimals, terminating decimals, and then you include your non-terminating 0.3 recurring, which is the third, but we can represent them as fractions, so they're rational numbers. We also have what are known as irrational numbers. They fill in the extra gaps there. They're special numbers like pi, like the square root of 2, the square root of 17. They're non-terminating, but they're not recurring numbers. Okay, and you've got special numbers like e as well, the exponential number. And these all fall into our number line, which we call the real numbers. Now, I like to look at them as the numbers on the number line. So if I have my number line here, oops, I think I can do a better line than that. Let's try again. Okay, so there you go. So that's my number line. Now the natural numbers, we got them, say 1, 2, and 3. 1, 2, and 3. But there's still gaps in between the numbers, and we haven't got a 0, we haven't got any negatives yet. Then we add the whole numbers on, so that includes the 0, 1, 2, 3. Then we can add integer numbers, which gives us our negatives as well. So you got -1, -2, -3. So those are our numbers so far, but in between these numbers we've got our fractions, and that's where the rational numbers come in. So your 2.5 here, or your a third here, 0.3 recurring, and that fills in most of the gaps then. So now our number line is continuous, except for these special numbers called irrational numbers. And they're very special. They prop up in nature like pi, or like the exponential number e there. They prop up in nature. And they fill in the extra little gaps that we have on our number line that make it continuous. It's just a bit of extra information for you. Right. Let's have a look at these rational numbers then. So like we say, a rational number is a number that we can express as a fraction. Okay? Fraction, a ratio of two numbers. All terminating and repeating decimals can be expressed in that way. So if they terminate or they repeat, then we can express them that way. So 4 out of 5, 2 2/3, which is the same thing as 8 over 3. Any of these numbers we can express as a fraction. 6, we can think of 6 as 6 over 1. Minus 3 over 1, and so on. 2.7 is 2 and 7 out of 10. Okay, so that will give us 27 out of 10. 0.7, 7 out of 10. 0.625, you can think of that as 625 over 1,000. Okay, as long as we can represent them as a fraction, then we've got their rational numbers. And we're going to look at numbers like 0.27 today and see how we can write those fractions out. Here we go. We've got a repeating decimal here, 0.142857. So it keeps repeating then. Everything from 1 to 7 repeats each time. And we can write that as 1 over 7. Because it's repeating, it's a rational number. Okay, so we got 0.6. You can think of that as 6 over 10. Okay, 3.8, 3 and 4/5. Okay, 38 over 10. 561 over 10, and so on. So these are terminating decimals, which are rational, because we can. So now we're going to show that a repeating decimal is rational. Now, as we've stated, our definition of rational numbers means that we can express the rational number as a fraction. So if we can express 0.33 as a fraction, then we can show that it is a rational number. So what I'm going to do is I'm going to let x be equal to 0.3 recurring. And then I'm going to say let 10x, I'm going to multiply x by 10. That gives me 3. That's a 0 there. 3.3333 recurring. Okay, so I've multiplied this equation by 10 to give me 10x, and multiplied this 0.33 by 10. Okay, let's move the 3 over there. So that's equation 1, that's equation 2. I want to get rid of the decimals. So what I'm going to do is I'm going to subtract equation 1 from equation 2. Let's write that there, subtract equation 1 from 2. So that's going to give us 10x. So let's draw a line underneath it here. 10x take away x gives me 9x. And then 3.3 recurring minus 0.3 recurring. The decimals go, leaves me with 3. That means x is going to be equal to 3 divided by 9. So x is equal to, if I simplify that, a third. So this means that because I can show that to be a fraction, 0.3 recurring is a rational number. Let's have a look at another example then, slightly different. This time it says show that 0.4545 is rational. So same again, let's let x be equal to 0.4545 and so on. That's the equation 1. And then this time, if I multiply it by 10, I get 4.5454. So the decimal will be different. So instead, I'm going to multiply it by 100. So 100x means that I'm taking the first two numbers over to the left-hand side. So that's going to be 45.454545, which is equation 2. So that means after the decimal, they're the same. So I can subtract again equation 1 from equation 2. Equation 1 from 2. Much the same effect. 100x take away x gives me 99x, which is equal to 45.45 recurring minus 0.45, which gives me 45. So x is going to be equal to 45 divided by 99. Can I simplify that? Well, if I look at it, 4 and 5 gives me 9. 9 gives me 18. They're both in the 3 times table. So 3 goes into both of them. 3 goes into 45, 15 times. And into 99, 33 times. And you just think that 3 goes again. So that's going to be equal to, if I divide by 3 again, 3 goes into 15 5 times, and into 33 11 times. So x equals 5 over 11. That means 0.45 recurring is rational, because I can express it as a fraction. So 2 examples, write them down. Hit pause, write them down. When you're ready, I want you to attempt 2 questions for me. Hit play again. Right, so 2 examples. I want you to have a go exactly the same way as before. Hit pause. When you're ready to go through the solutions, hit play again. Okay, so as before, we got 0.2 recurring, so we can write let x be equal to 0.222 recurring, and I'm going to multiply by 10, so I can move the 2 over there, so that means 10x is going to be equal to 2.2222 recurring. That's equation 1, that's equation 2. To get rid of the decimals, I'm going to subtract equation 1 from 2, and that's going to give me 9x. Draw a line underneath it. 10 take away 1, 9x is equal to 2, so x is equal to 2 over 9, which implies then that 0.2 is rational. Okay, so corrections in green if you need them. And then here, same thing again, let x equal to 0.6363 recurring. And I'm not going to multiply by 10 this time, because that just gives me 6.3636, which is a different decimal. So I'm going to multiply by 100 this time. So 100x is going to be equal to 63.6363 recurring. That's equation 1. That's equation 2. Get rid of the decimals. I'm going to subtract 1 from 2. I've abbreviated it this time, but I think you're aware of what we're doing now. Draw a line. 100 take away 1, 99x is equal to 63. So x is going to be equal to 63 divided by 99. And see that 3 goes into both the numerator and the denominator. So divided by 3, I get 21 divided by 33. Okay, so I've got my fraction. So that implies then that 0.63 recurring is rational. Rational. Good. So make your corrections, and then we'll have a look at 2 more examples then. Just to note, 3 can still go into the top and bottom, numerator and denominator, so that's going to be equal to 3 goes into 21 7 times, and into 33 11 times, so 7 out of 11. Okay. Okay, so we got 2 more questions. I think you can have a go at this yourself. So I think have a go, and then when you're ready to have a look at the solutions, hit play again. Okay, so we got 0.273. So 273 is recurring the whole time. So we could write, we can let x equal 0.273. I won't use the dots. I'll do 273 again, and so on, recurring. So now if I multiply by 10, I get 2.73273, so that doesn't help. multiply by 100, which is 2 zeros, I get 27. So I'm going to multiply by 1,000. So I've got 1,000x then, which is equal to, and that's 3 zeros, so I can move 3 numbers over. So it's 273.273 recurring. That's equation 2. That's equation 1. And so I'm going to subtract then 1 from 2. And that gives me then 1,000x take away 1x. Let's draw a line. So 1,000 take away 1 is 999. X is equal to, getting rid of the decimals, 273. So that means x is going to be equal to 273 divided by 999. 2 plus 7 is 9 plus 3 is 12. So that's the 3 times table. So let's see. 3 goes into 27 9 times, so 91 divided by 3 goes here, 3. So x is equal to 91 over 333, which is a fraction. This implies then that 0.273 is rational. Question number 4. So again, we say x is equal to, let's say let x. Let x be equal to 0.1234, 1234 recurring. So I need to take that 1234 over to the left hand side so that I can start again with 1234. That means I need 4 zeros, so I'm going to multiply it by 10,000. So 10,000 x, I've got my 4 zeros, is equal to 1234.1234 recurring. That's equation 2, that's equation 1, and I'm going to subtract again. Sub 1 from 2, draw a line. That gives me 9,999 x, which is equal to that, take away that, 1, 2, 3, 4. So x is equal to 1, 2, 3, 4 divided by 9999. Fraction. So the implication then is that 0.1234 is rational. Good. Let's have a look at some more examples. So hit pause, write these down if you haven't already, and then when you're ready to look at a couple more examples, hit play again. So these are 2 slightly different types of examples. So let's go through question 5 together, and then maybe you can have a go at question 6. So on question 5, it says show that 0.73 recurring is rational. So as usual, we let x be equal to 0.73 recurring. Now that 7 makes it slightly different because the 7 isn't recurring. So if I multiply by 10, so if I have 10x, that's going to give me 7.3333 recurring. So I can't, that doesn't help me because if I subtract, I'm still going to have decimal places. So what I need to do in this case is if I multiply it by 100, I get 100x is equal to 73.3333 recurring. So now this is my question, my equation 1, this is my equation 2. Both of them have got the 3 recurring after the decimal place. So if I subtract 1 from 2, I get rid of my decimals. So that's exactly what I'm going to do. Subtract equation 1 from 2. Draw a line here. And 100 take away 10x gives me 90x. So it's slightly different from before. And then 73 take away 7. Okay, so 73 take away 7 gives me 66. That means x is going to be equal to 66 divided by 90. I know 3 goes into both of those terms. 3 goes into 66 22 times, divided by 3 goes into 90 30 times. Oh, interesting. So 2 also goes into that, 11 times out of 15. So x equals 11 out of 15, which is a fraction. So that implies then that 0.73 is irrational. So what I want you to do is to write this down as an example and then have a go at this one. Okay? And when you're ready to go through the solutions with me, hit play again. Okay, so as before, we say let x be equal to 0.5888. And when I write with my x, I tend to show the decimal places. I don't tend to write it with the dot on top to show recurring, because it helps me when I multiply by 10, say, I can see what's after the decimal place. So that's just going to be 5.88888. Okay, that's equation 1. And if I multiply by 100 x, I get 58.88888, which shows me then what's after the decimals. And by subtracting 1 from 2, I get rid of the decimal places. So subtract 1 from 2. Draw a line here, and that gives me 100 take away 10, 90x, and then 58 take away 5 is 53. So x is equal to 53 divided by 90, which implies 0.58 is rational. So if you didn't work through that, write it down now, and then we'll have a look at another example. So hit pause when you're ready, hit play again. Okay, let's have a look at these two examples here. This first one, as usual, we're going to say let x equal 0.6585858. So in the first instance, I'm going to say multiply by 10. So 10x is equal to 6.585858 recurring. Now, so it's not 58 that recurs. So if I can get 658.58, which means I want to multiply x by 1,000 next. So I've got 1,000x is equal to 658.5858 and so on. So that's my equation 2, that's my equation 1. So if I subtract 1 from 2, let's just draw a little line here, then I get 990x is going to be equal to 658 minus 6 of 652, and the decimals, they subtract themselves and cancel. So x is going to be equal to 652 divided by 990, and I think 2 goes into both of those. We got 326 divided by 495. It's a fraction, so the implication then is that 0.658 recurring is rational. What I want you to do now is to have a go. Have a go at question 8. It's a very similar kind of question. So take your time, hit pause, have a go, and when you're ready to go through the solution, hit play again. Okay, so we got 0.174. recurring. That should be a decimal over the 4 there. Somehow it's managed to shift. Don't know how. Should be a decimal there. Good. So that means x is going to be equal to, let's put a decimal back there, 0.1747474 recurring. 10x is going to be equal to 1.747474. So I'm managed to get my recurring decimal there. And then to get the 74 over to the other side, I've got to multiply x by 1,000. Because I need these 3 terms, 1, 2, 3, so I need 3 zeros. So 1000x is equal to 174.747474. That's my second equation, that's my first equation. So I'm going to subtract 1 from 2. And that gives me 1000 take away 10, 990. X is equal to 174 minus 1, 173, because the decimals cancel each other out. So x is going to be equal to 173 divided by 990, which means that 0.174 is rational. So hit pause. Just make that, there we go. Oops. There we go. Hit pause, make your corrections or write the examples down, and it's your turn now. You can do some classwork for me. Okay, and your classwork then, sections D and E. Okay, off you go. Good luck.